So we'll get started. I'm going to be talking about something called polynomial chaos. The word chaos is interesting. It's not about chaos theory as we describe it now. Chaos used in the early 20th century was often used by mathematicians to describe stochastic processes, so that's what we're going to be talking about. If you wanted to follow along with this talk, at the URL up there, you can download the IPython notebook and run it alongside. More than free to do that. But I'll be going through, and this is basically an introduction to this topic called polynomial chaos. It's not very common in most data science fields, but it's used a lot in certain engineering disciplines. And the motivation behind polynomial chaos is that it allows us to quantify uncertainty in parametric systems, which is something that we might do as a data scientist if we have a model and we want to understand how randomness affects that model. So just a few notes about what I'm going to be talking about. This talk is tagged at expert level. I will be talking about some advanced mathematics. You don't need to understand it to appreciate what's going on, but I'm not going to have time to go through a setup and explain all of these concepts. So just to give, judge the audience, where your comfort level is. How many people here have heard of the radon-Nikodym derivative? Okay. It's fine if you don't know what that is, but that's the basis of the math that I'm going to be talking about. I'm not going to be doing Q&A after this talk. If you'd like clarification on the slide, please feel free to interrupt me, or please feel free to talk to me in the hallway afterwards. I prefer it one-on-one rather than trying to address what is the equivalent of 2 graduate level functional analysis courses in a quick question. And a final warning, I am a C# developer by training. I write Python a bit like a functional programmer. I'm not sure where that came from. I try to minimize that a little bit, so I'm not going to be doing a lot of MapReduce, but I will be doing some currying, stuff like that in the code that I write. And I have one really horrible line of code that I'm going to apologize to you for right now. So, as I mentioned, polynomial chaos is a way to represent random variables or random processes in terms of orthogonal polynomials. And this is maybe a little bit of a foreign concept, but we're all probably familiar with PCA, principal component analysis, to some degree. Principal component analysis, basically what we do is we take an operator, which in this case is the covariance matrix, we diagonalize it through a process over a finite dimensional vector space. And what PCA really is it's a special case of what's known as the Kosambi-Karhunen-Loew transform, which is sometimes called a spectral expansion of a random variable. And all that is it's writing a random variable in terms of an eigenfunction basis. And in PCA, we choose the eigenvectors of this symmetric matrix to be our eigenfunction basis. Polynomial chaos is the same thing, except we're choosing orthogonal polynomial families. So polynomial chaos is really the simplest way to think about it would be like PCA over an infinite dimensional polynomial vector space instead of a vector space of reals. So visually, we look at this, and I promise this won't be all math. I'm going to get to Python, but I do have to do a little bit of setup. The KKL transform looks like this. PCA, what we're really doing when we invoke SciPy is just this series on the bottom here. And you don't have to understand the notation or worry about what it is. It's really just to look at what the form is. Polynomial chaos is very much the same thing, where we take a random variable x, or a random process x, and we decompose it in terms of deterministic coefficients x sub I over orthogonal polynomial basis phi sub I, and that orthogonal polynomial is going to be written in terms of a random variable that we choose. And that's the most important, that's the core thing of what polynomial chaos is. Why would we want to do this? Well, in practice, when we look at the distributions that we see in our data, whatever it is that we're analyzing, it could be customer data, ad data, network traffic data, these distributions very rarely look like the canonical distributions of real life, or in theory, rather. You never really see something that's truly Gaussian. You never really see something that's truly uniform. A lot of times you look at data and it's got this bimodal and you're like, oh, well, what am I supposed to do with that? So this technique allows us to do a few things. We could use it to accelerate Monte Carlo simulation. We can use it to handle distributions that are really messy in terms of distributions that we can control. So we don't need to try to figure out what the distribution of our data is in our database in order to do modeling on it. We can just say, well, I'm going to represent it in terms of a polynomial chaos expansion. Oh, that didn't really render very well. But basically what it is the mathematics behind it, some very interesting math that came out in the mid-20th century, a theorem by Cameron and Martin. Basically, one of the consequences of it is that this representation, that infinite series that I displayed, is going to converge in the limit and the mean sense to the distribution that we have. And so what we can do is we can use a polynomial chaos representation to represent any arbitrary probability distribution using only Gaussians or using only uniform random variables, as long as that target distribution has a finite second moment, or finite variance. Just quick question, can anyone tell me a distribution that doesn't have finite second moment? Does anyone know of one? Cauchy distribution, it's a canonical one. In simpler terms, we can represent random variables of arbitrary distributions by writing a polynomial chaos expansion, and we get to choose which distribution we write it around, which is a super powerful concept. This is like doing a Taylor expansion for a really nasty function. We just write it in terms of a polynomial, and we truncate it, and it's very simple. All right, so basically, let me make this a little bit smaller so it renders better. So there's a natural relationship between orthogonal polynomials and probability distributions. And this is the orthogonality condition for the Hermite polynomials. Orthogonality, just like in a vector space, is written in terms of an inner product. We call it a dot product when we're working in finite dimensional vector spaces. But what this is the inner product is written in terms of literally the product of two functions times a weighting function. We integrate that over the domain, and then we get something that comes out at the end. And in this case, we're writing it in terms of the Kronecker delta, which means that if our two functions, hi and hj, if I is not equal to j, then the orthogonality says that that inner product is equal to 0. But if you notice the terms in the red here, let me scroll over, that looks really familiar, right? That term looks super familiar. And in fact, what that is that's just our standard normal probability density function. So the Hermite polynomials in this case, their orthogonality condition is written in terms of this standard normal distribution. So we can use this to represent basically any finite variance random variable. In this, I'm going to change nomenclature here. I'm going to call it k. Writing it in terms of a series of Hermite polynomials about a Gaussian. So if I have some random distribution that represents my customer data, I want to represent it in terms of a series of Hermite polynomials, and then I want to compute these deterministic coefficients. So this is just like doing a Fourier transform, where we know what the form of the function is, we just need to get the coefficients. That's what the exercise is all about. So we can do this using a technique known as the Galerkin projection. So we take that series, and what we're going to do is we're going to take the inner product of that series, and first we're going to take the inner product with the first orthogonal polynomial, and then the second orthogonal polynomial, and we're going to do that all the way up to infinity, or we're actually going to truncate it at p. And so what you get is an expression that very deterministically tells you what these coefficients are, these ki's. And so you get this integral that comes out. It's the 1 over the orthogonality condition times this integral in terms of a Hermite polynomial. The problem is that this integral is actually kind of mathematically meaningless because we don't know what k is. If we could write k in a closed form, we wouldn't be doing this exercise at all. So what we're going to do is we're going to do something called an inverse sample transform. We're going to move zeta and k. So zeta is our Gaussian random variable, and k is our nasty random variable. We're going to move them to the same uniformly distributed random variable. And we can do that because they're fully dependent. So kind of breezing through this here to get to the code. We transform both of these onto a standard uniform distribution, and we put that into the integral. And now we have this form on the right, which is very easy to compute. This is something that we can write code for very easily. It's just the inverse CDF of our target distribution, which we can compute, we can approximate numerically if we want, times the polynomial, now evaluated over the inverse CDF of a Gaussian. So that allows us to compute these coefficients. We're going to do this p times, get all of these coefficients, and then that's all we need to do in order to represent our random variable in these forms. So there's a few ways that we can compute this orthogonality condition. It has a closed form, basically just a factorial. There's a few different ways to handle this in practice. Either you can just compute the factorial, which I didn't do because I've written a factorial function about 1,000,000 times in my life and I was bored. We can choose, in practice, normally what we do is we actually rescale zeta so that the orthogonality condition comes out to be just the Kronecker delta. Or we can just compute the integral using a Gauss-Hermite quadrature, which is basically prepackaged to fit the problem that we already have. So now we're pulling in this very standard integration technique, and it's hand-tailored for the problem that we have, which is very, very cool. So we're going to do that. Okay, and that's all the math setup. So I'll take a break there, and if anyone wants me to go back to anything, let me know right now. That was a huge amount of here's 2 semesters worth of math dumped on you in your lap. Okay, so just to recap, what we're going to do is we want to represent a random variable k in terms of a Gaussian. So I'm going to choose a uniform distribution. I'm going to represent it in terms of a Gaussian by computing these ki coefficients and then reassembling it at the end. In order to do that, I'm going to run some Python code. We don't need a lot to make this happen. In fact, half the code up here is just to make the plots work. So we're going to use NumPy. The Hermite polynomials are already built into NumPy. That's really convenient for us. SciPy stats, I'm importing norm from there because I just didn't feel like writing the inverse CDF function when I could just import it. There's a really interesting representation, rational function representation of the inverse normal distribution, if you're ever curious. I don't know where it was computed back in the 30s, and it has these just arbitrary numbers that some poor grad student had to compute someday. Yes, I can. So we'll run that. And then, so what I'm going to do here is a couple of utility functions. I'm going to define a method that really just gives me the coefficients for the ith Hermite polynomial. All this is just a vector of zeros with the nth term being a 1, so that represents h2, h3, h4, whatever. And then a utility method for the inner product. I'm just going to use it to smush together 2 Hermite polynomials, use the built-in library to multiply them together so I don't have to do all of that work, and then I'll return a function for that. So that's pretty basic. And then I'm going to set up a basic trapezoid integration method. This is your standard method from numerical analysis. There's nothing fancy about it here. It's actually probably pretty horrid. So we'll just skip over that. So what I'm doing in this slide is I'm going to build a couple of inverse distribution functions. And I want to parameterize them. In this case, I only really parameterize one of them, the uniform distribution. But these are really nice, easy things closed form things to write, except for the normal, which I use SciPy for. So I'm going to use these to generate the coefficients. And that's what I'm going to do in this kind of nasty block of code. So I'll walk through this really quickly. So we're going to take in an order, truncation order P, and we're going to take in our target distribution's inverse CDF H. So once we do that, we're going to pre-allocate the KIs. The reason I'm pre-allocating here is because I want my code to match the math. I don't want it to be idiomatic Python, because if you want to go through and look and say, wait, how did they do this? I want the code to match the math that I'm presenting and not like some awesome list comprehension that takes you 20 minutes to decompose. So I'll pre-allocate the KI array. I'll set up the Gauss-Hermite quadrature. That's also a built-in method in the NumPy module. And then, so what I'm going to go through is for each term, I'm going to compute the inner product, which can be done by just computing the value of the inner product multiplied together here at each node times each weight. That's your basic Gauss-Hermite quadrature. We take the sum. And then for the integrand, I'm going to set it up so that's where we have h of u times the Hermite polynomial of the inverse CDF of a Gaussian. And that's all we've got. And so now the Ki is computed simply by performing this integration, this trapezoid, I'm using the trapezoid integration method here to compute that integral. And now you see, this is, the way I've written it is we take the integrand as a function, our bounds, our upper and lower bounds, and then the number of points in our partition. We want to compute the integral over 0 to 1, but with the normal PDF, or the normal inverse CDF rather, if you put in 0 and you put in 1, you're going to error out because they go to infinity. So we have to pull it in a little bit for numerical stability. So now that that's set up, we can actually just compute these coefficients. But then I'm going to also define a method that's going to build out that random variable from those coefficients for us. So all this is doing is it's taking the coefficients, it's multiplying them by the polynomial, and it's adding them all up. So, whoops, did I run that code? I did run that code. OK. So now we'll generate some Gaussian random variables. We'll generate, I don't know, say 5,000 of them. And then we'll go ahead and we'll build out this distribution. And this takes just a second. So that's pretty good. So what we're doing here is we're building a uniform distribution from Gaussians with a 13th order expansion. But if we change the order of this, we can see what happens. Like if we take it from 2, that's just our Gaussian distribution. And as we get the order, as we increase that order, we get more and more like a uniform distribution. So it's really sufficient to truncate these expansions, add a pretty small number of terms, and this is pretty good. You wouldn't like build a random number generator around this. It's not that good. But if you had a really nasty distribution that you really can't describe with good closed form mathematics, this is a really quick and handy way to do it. And just to go over what those KIs are, this is what's really interesting. Once you compute those KIs, what we'll do is we'll take a look at the first one. This is a 0th order coefficient. This is the mean of the standard uniform distribution. Your 0th order coefficient is always going to represent your mean, and that's going to become a powerful concept in the moment. But the other interesting thing is that the second coefficient, k sub 1, is always going to represent your standard deviation. So the standard deviation of a standard uniform distribution is, if you recall the formula, it's going to be basically standard uniform is the square root of 1/12. So it's very close. So that second coefficient represents your standard deviation. First coefficient represents your mean. So now we have a very good way of using this to represent the statistics of a process without having to do a bunch of simulation. And that's what I'm going to do next. So just to show you that this works for other distributions as well, we'll use an exponential distribution, see what happens. That's pretty cool. We can build that out like that. And if we change the order, we'll see the same type of behavior. The lower the order we get, the more it looks like a normal Gaussian distribution. And the higher we go, the better it looks. So this is exactly the behavior we want. We want this convergence behavior as we increase p. So the question is, do we need to use Gaussian random variables in this process? And the answer is no. There's a scheme called the Wiener-Aski scheme. And you can actually use, there's a whole family of orthogonal polynomial distributions that you can use to do this. So if for your problem, the uniform distribution is better, we can use that. If for your problem you have a discrete distribution, you can also use it around discrete random variables. And what's really interesting is that all of these orthogonal polynomial families are related in terms of what's over here on the left here, the confluent hypergeometric functions. So it's like this whole family, and basically you can bootstrap, starting from the Hermite polynomials, you can bootstrap up to represent any distribution you want if you know how those functions work. So I'm actually just going to skip this slide. That's about doing it for discrete distributions, but in the interest of time, I'll go over that. So let's give a practical example. Suppose we want to solve a differential equation like this, and suppose it's parameterized by k, and k is a random process. Say this represents the attention rate on our website, right? We know that the amount of time somebody spends on the website falls off like this, and we've built a model for that, but it's that k is a random parameter. So we could solve this differential equation for a specific k. That's pretty easy. We'll just build out our standard Runge-Kutta fourth order method. And if we solve it, it looks something like this. I guess it doesn't want to scroll on me. That's all right. So suppose that we want k to be a random parameter, and you can't read it because the displays have messed with the windows here. But it's going to have a support s, and it's going to have a distribution function f of k. And the mean of that random parameter is going to be k bar. So we might think, okay, is this the mean of our solution? Do we just solve the differential equation and throw the mean of the random parameter in there and say this is the mean of our output response? We do this a lot in data science. We say, okay, well, we've got this ugly distribution. What's the average customer look like? Okay, now I'm going to use the average customer in my model and say that is, because we're using the average customer, I throw it into the model, that's going to be my average output, right? Turns out that's not actually the case. And if the stochastic mean, if that's what you really want, looks more like this, which is really hard to compute, especially if you have a really nasty distribution. So we don't want to do this. This is not a productive thing to do. So we're going to use a few different techniques. One of them could be a direct Monte Carlo simulation, which I'm going to do here. So we're going to generate 1,000 samples of this solution to this ordinary differential equation. And it's going to run and run and run. That's a fourth order Runge-Kutta integrator, a standard method for solving ODE. It takes about a minute. The suspense is purposeful. So we can see already that this is like not really what we want to do. This is not the best use of data scientist time, running direct Monte Carlo simulations, because that's only 1,000 samples, which is not enough for statistical accuracy, of the most simple ordinary differential equation you can get. And like, yeah, my Python code is really not the most optimized for this, but 20% of that time was still a lot of time wasted, right? So if we take a look at, I have seemed to have lost my scrolling capability. There we go, it's back. So this is our mean, the mean of our solution in the blue, and then we have our upper and lower 95% confidence intervals. And now we can say, aha, now I can simulate my model for my customer attention on my page. But that took a really long time. And just for comparison, this is the stochastic mean versus the deterministic mean. So if you actually throw in the average of your random distribution and expect it to be the average of your output, That's the red line, which does not actually match the mean of the Monte Carlo simulation. So we actually don't want to do that. So we can use polynomial chaos to make this easier, easier being a relative term, considering I just threw an entire book of functional analysis at you. But we've already done this work for k, right? We've already built out k, so now we want to do it for our differential equation y. So what we're going to do is we're going to gather these terms. We're going to this is called an intrusive polynomial chaos representation. We're going to take the polynomial chaos representation, throw it into our differential equation naively, and then we're going to do the same Galerkin projection as we did before. We're going to gather the terms, and now we have this really nasty looking thing, which is actually not that complicated to compute. So that triple product can be easily computed with the Gauss-Hermite quadrature. That what's being overwritten there is that this term here, the three phis in a row, that's just an inner product. So we can use our Gaussian quadrature to compute that in very few computations. We only need maybe 50 computations in order to compute that integral. So that's super easy. And then with the inner product, we've already computed those, so that's easy. All we need to do is generate them. And so what we get as a result of this is going to be a system of differential equations. It's going to be a linear p by p matrix. So we're going to, instead of solving 1,000 differential equations of first order to generate our Monte Carlo analysis, we're going to solve one differential equation of pth order, which is a huge improvement in speed. Basically what we're saying is we can generate as many samples as we want using only p solutions to a system versus 1,000, 10,000, a million. So we'll set up that triple product as a nice little utility method here. And then here's the meat and potatoes of it. So we're going to represent this system. We're going to do a fifth order expansion. We're going to solve that differential equation that I displayed earlier for a uniform random k. And we're going to compute the statistical moments of that distribution and compare it to that Monte Carlo simulation that took a couple minutes to run. And that's it. Our solution is already done. So to prove that, I'm going to plot, this is the mean of the Monte Carlo simulation in blue. The dashed line is the polynomial chaos representation. The green line is it's 3 standard deviations from the mean. Red line is 3 standard deviations under the mean. Dashed line is the polynomial chaos. And so what we see is that in a fraction of the time, we got pretty good results with a pretty low order approximation of what we're actually trying to do. That's like a orders of magnitude reduction in computational complexity to get the statistics that you really care about. And so just to wrap it all up, this is the ugly line of code. Don't read this. I'm embarrassed by this. It's going to take just a moment to run. I'm actually going to generate the Monte Carlo samples for the polynomial chaos representation just to show you what they look like compared to the direct Monte Carlo simulation. And it's not exactly perfect. It's actually really imperfect because polynomials are really nasty to work with. And we're not guaranteed convergence to the entire solution space. We're only guaranteed convergence in the limit in the mean sense. So this takes a minute, but it's not as fast because I truncated it at 500 samples. OK, so that's done. So if we plot this out, these are our confidence intervals. Let's see if I can't scroll this here. I don't know what it is that has made me unable to scroll. Yeah, there we go. So what we see is like the polynomial chaos expansion goes like really high, and then also really low into values that don't make sense. It doesn't make any sense for the solution of an exponential decay to go under 0. That is nonsensical. So we don't actually use that sampling to get our statistics. But if you look at the mean of that Monte Carlo simulation, the mean is very close to the direct Monte Carlo simulation mean. And again, this is only with a fifth-order polynomial chaos expansion. So with very few lines of actual meaningful code, and this is all of the meaningful code that exists in this modeling approach. Basically, with this code here and the associated code to compute the KI coefficients, we've taken the burden of trying to understand how our really nasty distribution affects our random process and brought it down to a very basic, very fast computation. I'll even run it again. And it's done. And so we can do that for any distribution we want that has finite variance. That's all that I have. I hope that was a decent introduction. I will actually take a couple questions since I think I have a bit of time. So if anyone has any questions or would like a clarification on any of this, I see some blank faces. Yeah. Oh.
You do question now.
I'll do a couple questions.
Okay.
Yeah.
Thank you. That was interesting. Just for P, are there any results which tell us what P you should use, or at least bounds or whatever, which will give us some interesting intuitions for the different distributions and so on?
So the intuition that I used was, before we start throwing this solution at our process, I throw it at generating the random parameter itself. And we'll go back to where I do that. So there's not like a general rule for choosing P, but what I do is I just start increasing it until this thing looks like the thing that I have. And this is a very low-cost computation. This takes a matter of seconds to run.
Yeah, great talk. Thank you. So you said the first coefficient is like the mean.
Yes.
The second one is like the standard deviation.
Yes.
Is there any such interpretation for like all the other coefficients, like kurtosis, whatever?
Yes, they represent the higher moments of the distribution with respect to the distribution that you're using to model it. So if you used, say, a Gaussian distribution to model another Gaussian distribution, like a standard normal to model a Gaussian with some different variance, what you would get is mean, variance, and then the rest would be 0. Because you don't have like a skew or a kurtosis when in that sense.
Alrighty. So thanks a lot. I think I have a question on the inverse sample transform that you do. So you said that the two variables k and zeta are fully dependent.
Yes.
And therefore you can do that. How does it work again? I think I'm lost there.
Okay. Right. So let me get back to that. Yeah, so this is the magic. This is the magical slide. So recall that a cumulative distribution function is, the range of it is always between 0 and 1. And what we're going to say is that if we compute the cumulative distribution function of a random variable, we can treat that as a distribution over the support 0 to 1. And when we're supporting something over 0 to 1, the most natural and simplest distribution we have is the uniform distribution. We could choose another one that's supported on 0, 1. But the uniform distribution works very well. So we're going to say that the CDF, the cumulative distribution function of our Gaussian, which maps to 0 to 1, we're going to call that U. and the cumulative distribution function of our parameter k, we're going to also say that that's equal to u. And we can do that because we're declaring that these random variables are fully dependent. So we can say that we're going to map them to the same thing. And then once we've mapped them to the same thing, then we just take the inverse CDF of each. And we'll give those, here I just defined them as H and L. And now what we have is k written in terms of u, and we have zeta written in terms of u. And the reason that we want to do that is because this integral on the right-hand side, k and zeta are not written in terms of each other right yet. We need to get them written in terms of the same thing in order to compute this integral in a meaningful way. So we're basically doing a change of variables on two different variables and putting them into the same space, recognizing that they are fully dependent. Do one more.
One last question, and then it's over.
Yeah, I was wondering whether you, in your example, you had this exponential decay where the decay constant k is a random variable, but it was constant in time, kind of, right? So, does this whole approach work when your random variable is also dependent on time? For example, in a classical stochastic process.
Yes, it does, and it is substantially more complicated.
Okay. And very, very final question, does it also work for discrete random processes?
Yes, it does. So I breezed through that, but let me actually go into that a little bit. So this inner product representation, this orthogonality representation, here, this is a Riemannian sense in that we're taking the two functions, we're multiplying them by a weighting function and integrating over their independent variable, right? What we're actually doing here, though, is if you look at this exponential term times that the differential there, that's actually a measure. So if we look in a Lebesgue-Stieltjes representation, what we're actually doing is we're computing an integral over, the inner product is just a computation over a measure. And as it turns out that this Gaussian term here, that's just the radon-Nikodym derivative of a Gaussian measure. So we can generalize this to a discrete distribution and then use measure theoretic concepts, and just, it's the same thing. But of course, if we have a discrete measure, or a counting measure, then that integral just becomes a sum. So then we just do the same thing, but it's simplified, it becomes a sum. All right, that's all I'm going to do for now. If you have any other questions, feel free to find me. I'll be around for the rest of the day. Thank you.